Hello and welcome to my YouTube video. Today I'd like to give you an introduction to the world of chess programming. Before discussing any flashy topics like techniques to begin evaluating positions, we first need to talk about the way to represent a chessboard and its pieces on a computer. Primarily, this is an issue of selecting the appropriate data structure. There are many different approaches, and I would like to start with, in my opinion, the most intuitive, the mailbox approach. In the mailbox approach, each cell on a board has its own addressable space in memory, usually represented as a two-dimensional matrix. This technique is square-centric, where pieces are primarily addressed and stored in this matrix, and indexing is done in the same way you would visually look at a chessboard. Choose a file and rank, and return the piece's data. This approach is the recommended strategy for newcomers to chess programming, as it is both the easiest to implement and maintain. While the mailbox approach uses a square-centric technique, we can use the inverse association of a piece-centric approach with piece lists. In this strategy, we take a basic list or array data structure in code and store all the pieces currently on the board, each associated with a specific rank and file. This makes iterating through pieces to generate their legal movement much easier, as you don't need to spend extra computational power checking possibly empty cells within a matrix such as with the mailbox approach. However, on the opposite end, indexing the destination squares of these pieces in a piece-centric approach requires iterating over enemy pieces, which would usually be a constant lookup for a square-centric technique. Both of these approaches have other surpluses and deficits that I have not mentioned, as well as hybrid approaches that make use of the upsides of both data structures. However, there is another strategy that is by far the most popular way to represent a set of pieces on a chessboard, and that is with bitboards. Bitboards are a piece-centric technique similar to the piece list strategy. However, instead of using composite data structures for each individual piece, we take advantage of the computer's hardware, set theory, and bit manipulation tactics to store pieces of specific classification within single 64-bit variables. A bitboard has exactly 64 squares. We start our process by classifying a single finite set of length 64, with each element being associated with a square on the board. The presence of a square in this set represents that square's vacancy. These sets have meaning when we use them to describe a certain relationship between the pieces. So, for example, if we say that the set as a whole represents a square on a board that a knight occupies, the start of the game might look like this. By performing set algebra on sets of differing classifications, we can represent more complex relations. For example, suppose we have two sets, A and B. A is the vacancy set of all black pieces on the board at the start of the game, and B is the vacancy set of all rooks on the board at the start of the game. By taking the set intersection of both A and B, we are by definition returning everything in common in both sets. In this case, it means the intersection of sets A and B shows all black rooks on the board. In fact, this type of set intersection is a very common operation that will occur considering the manner in which we define our positions bitboards. This set's hardware representation will be a single 64-bit unsigned integer, which, in situations like this, will be called a 64-bit word. The only information we will be considering for this word are its bits, where each bit's on-off state represent that square's vacancy on a chessboard. This word is what we refer to as a bitboard. Through the use of bitwise operators, it is possible to operate on bitboards in a similar way as a vacancy set. Because computers already store all data in a binary state, as well as the fact that 64-bit processing architectures support operations on variables of up to 64 bits, a bitboard approach lends itself to being extremely performant. By this technique, only 8 bitboards are necessary to fully represent the vacancy of every single piece on a chessboard. 6 are required for each type of piece: pawn, knight, bishop, rook, queen, and king. Then 2 more for each color, the black and white sides. Through set operations, we can determine all the information we need for evaluation and make move functions down the line. Now that we have a way to represent all pieces on the board, it is possible for us to generate their movement. There are many strategies on how to generate the movement of pieces on a board, and what I will be discussing will be the generation of pseudo-legal moves. Pseudo-legal moves are moves in which you generate moves will not take into account the exact legality of the move, ignoring things such as king safety via pings and checks. I would personally categorize chess pieces move generation algorithm into one of three categories: lookup pieces, sliding pieces, and pawns. The first category I would like to talk about are lookup pieces. Lookup pieces are pieces in which it is not necessary to receive information from other pieces on the board, friendly or otherwise, to properly compute its pseudo-legal destination squares. Knights and kings are the only pieces categorized in this fashion. There are really only two feasible ways to implement a move generation algorithm for lookup pieces. The first is by calculation, where you perform a bit shifting operations relative to the piece's origin square. The second is to pre-calculate all destination squares indexed by its origin. In this situation, there is no real reason to choose to calculate the destination squares as opposed to doing it pre-calculated, unless there is very specific space implications. Implementing this is the most straightforward of the three categories of move generation algorithms and will not be discussed in further detail. Similar to lookup pieces, pawns have a predetermined number of places they can move relative to their origin square. However, their movement does depend on the vacancy of both enemy and friendly neighboring squares, direction, rank, and even the beloved en passant square. While it is possible to pre-calculate a destination square mask relative to its location, the optimization implications compared to calculating it during runtime are either non-existent or negligible in their difference, and in my opinion, not worth consideration in this video. I would now like to talk about sliding pieces. Sliding pieces are characterized by their ability to cover varying distances across a chessboard, depending on the presence of both enemy and friendly pieces. The three sliding pieces are bishops, rooks, and queens. Sliding pieces are arguably the most complex algorithms out of the three categories, as there has been an enormous amount of effort in optimizing the algorithms for bitboards. The first approach a developer might take to implement it would be, for each direction valid for its requisite piece, iterate through that direction until you reach an enemy piece, a friendly piece, or the edge of the board. This does end up being somewhat of a naive approach, however. Through the work of many people smarter than the author of this video, you can actually return a sliding piece's destination squares with a single lookup operation through the use of something called magic bitboards. A single lookup for every combination of origin square, friendly square, and enemy square input? If we were to have a single lookup table for every possible combinations of these inputs, we would end up with astronomically large tables, taking up quintillions of zettabytes in space. In comparison, the total of both the knight and king lookup tables require a total of 1 kilobyte of space. Luckily, there are many strategies in our tool belt we can use to optimize the space we require for our lookup table. When casting the direction of a sliding piece, it is not entirely necessary to take in the input of both friendly and enemy pieces. Both friendly and enemy pieces act as blockers to the piece we are moving. The only difference is that if it were an enemy piece, the player can capture that piece while moving to that square, while a friendly piece cannot be captured. With this logic, we only need the origin square and a bitboard of blockers, which hold the union of all friendly and enemy pieces. We can pretend in that case that all blockers are capturable and subtract all friendly pieces from the resulting attack squares. By doing this, we have reduced our space implications to a mere 8 zettabytes. Still not quite feasible to store on your home laptop. However, there is room for optimization. Our next observation might be that our lookup table is indexing this array by many unneeded vacancy bits in our blocker bitboard. If we are indexing our lookup table, we are checking squares not even in the path of where our sliding piece might move. What we can do is create a mask over those squares and index our lookup table by whether our mask squares are occupied. This drastically decreases the size required for our table and now only requires 2 megabytes. Woohoo! So we did it, right? While 2 megabytes is a perfectly reasonable amount of space to require for a lookup table, we unfortunately now have a new problem. When returning our masked bits, the possible configurations in which the spaces are occupied is spread across the entire 64-bit range of our masked blocker bitboard. The solution to this problem is through the use of a hashing algorithm. In essence, a hashing algorithm takes a key, our masked blocker bitboard, and returns the value associated with that key, our destination squares. What the algorithm itself does is turn our key into an index with a smaller size. In our case, this allows us to flatten out our input into a size manageable enough to store in a table. What is of utmost importance to us when implementing our hashing algorithm is speed. In order to ensure the speed of our lookups in our table, we must be certain that when flattening, also called hashing, our table into an index within that table, that index does not match any other indices within that table. When this happens, it is called a collision, and while not the end of the world, does have additional space and time implications with our move generation algorithm. If we were to make a single hashing function in which we are certain there will never be any collision with other values, it is called a perfect hashing function. In our application, this is actually a very feasible expectation. Our hashing function can actually be summarized into a single line of pseudocode. While short, this has a lot going on here, so let me explain. First, blockers is a bitboard of all occupied friendly and enemy pieces masked by our original piece's possible destination squares. By its nature, this will be sparse in terms of the number of bits that are set to 1 as opposed to 0, due to the mask. If we add some entropy to this value by multiplying it by a large enough number of arbitrary value, more bits within that blocker's bitboard will most likely be set to 1, which has the potential to give us more of an abundant set of zeros and ones. This number we are multiplying the blocker bitboard by has special properties and is almost always a unique number for each origin square of our piece. Multiplying our blockers by some random number doesn't always give us the result we're looking for, but once a set of values are found, it can continue to be used throughout the application's lifespan. Through trial and error, or through researching online, these numbers can be calculated or found and are actually cheap enough to calculate upon startup of your chess application. Once we populate our bitboard, we then collapse all of the bits to the right until we only get the most significant leftmost index size number of bits of the word. While it is possible to shorten the index size to a fewer number of bits, most of the time it will be 12, which is the smallest number of bits our directional bit mask will contain. Finally, this is what our magic lookup operation will look like once fully implemented. The hardest part of this whole process is actually finding the magic numbers necessary for the program, which essentially involves using the slower iterative solution shown previously to programmatically check if a magic number works or not, and then adding it to the magics table once found. Also, there's actually an additional benefit to using this hashing algorithm that I have yet to mention. If you look at our move generation algorithm currently, you may notice that we have some duplicity in our result set when entering different occupancy masks. Depending on the way you implement your hashing function, you can allow collisions of input with your occupancy mask as long as the destination squares return to the same value, which allows your tables to be even smaller than the 2 megabytes as stated earlier. It does require some more rigorous testing to find good enough magic numbers, or magics, to reduce the size of your index size variable, but it is an unintended consequence of our algorithm. There are many different ways you can write and develop the game of chess in code. This video is meant to take a peek at some necessary background if you wish to write a version of the game at a computationally efficient level. And even then, there are many optimization improvements you can make for your internal representation to be even better than the explanations I gave in this video. I simply hope that this serves as an adequate introduction to that side of chess computing. I hope you enjoyed the video, and have a good day.